alaikum. So now I would like to give a tip on a bit of electricity questions from the past papers. So this question states that figure 8.1 shows how the electromotive force of a 60 Hertz alternating current AC power supply varies with time. So this is how the variation of your electromotive force varying with time. And so the question is, calculate the time period of the AC. Right, so in order to calculate the time period, we know that frequency and time are inversely proportional. So T is equal to 1 over F. So in this case, you have the frequency, which is hertz. So time is equal to 1 over 60 hertz. And that is 0. So the period is going to be 0.017 to two significant figures, 0.017 seconds. Okay. Now, so figure 8.1 shows this power supply connected in a circuit. So you have this power supply that provides an AC current. It is connected to three different components, A, B, and C. State the name of the component A. So you should be very familiar with all the symbols of the electric devices. And this is semiconductor diode. So the answer here, this is a semiconductor diode, or you can just say for short, this is diode. Right, so in each time period of the AC, 1.5 times 10 to the power of 17 electron pass through a component A. So this is the number of electron that passes. The charge of the electron is 1.6 times 10 to the power of negative 19 coulomb. So the question is, calculate the average current in the circuit during one time period. So we know that current, so he's asking for the current. Current is equal to the charge passing over time. This is how we define current. So it's a number of coulombs, or the number of how much charge has passed over a specific time. We have got number of electrons, so the total charge of this number of electrons is going to be their numbers multiplying by the charge of each. So it's 1.5 times 10 to power of 17. This is the number of the electrons times 1.6 times 10 to the power of negative 19. And you do the multiplication here. So what you get is 2.4 times 10 to the power of negative 2. And this is, in fact, you can write it as 0.024 ampere. Or in fact, you can write it as 24 milliampere. So you can always write it as 24 milliampere, but it's preferred to write it in the SI units. Right, so in figure 8.3 given here, which is the same circuit that has been used before, with an arrow label E, mark with an arrow label E the direction of the electron flow through the component B. So through the component B, then you have two options. Either the current is passing through this direction, or other way, coming from from the other side, because this is an AC current and it produces AC source that produces current in both directions. But you have a very special component, which is the diode here. And you know that the diode allows current to pass only in one direction. And that direction should definitely be in this way. Since this is the anode, this is the cathode of the semiconductor diode. So this has to be connected to the positive part of, so it will allow only when this source act as the positive part of here, and the current coming from this direction. So I would say it allows current only. This is the forward bias current. So this is the current passing through the component B. I will label it through as E, or it's better you label it as B after has passed the component B. And in the second question, mark with an arrow labeled I the direction of the conventional current in the component C. Now remember, this source is producing two currents in two different ways, but the conventional current is known to be when the flow of the current is going from the positive terminal outside the battery towards the negative terminal. But this kind of source is producing two directional current. So it gives current in this direction, and it gives current in this direction. But remember, you have a diode in here, and the diode will allow only current to pass in this direction. So again, so this is the current going to pass through the component C. Right. So in figure 8.1 shows a circuit, the same figure, or without the semiconductor diode, with the components B and C connected to a direct current DC. Now you have a direct current DC power supply of an EMF 12 volt. So the current in this 0.3 is 0.3 ampere. So the question is, calculate the power delivered by the power supply circuit. Remember, this power supply has an EMF of 12 volt. So the power provided by this power supply is going to be defined to be I times V, and the current is 0.35 ampere multiplied by 12 volt, and that gives the power in watt, and this gives 4.2 watt. So the answer is 4.2 watt. 4.2 watt. So 2 marks each for writing the law and